Thank you for the invitation. And I have an allergy this season, so I might suddenly start sneezing. But like all my deadlines, it'll also pass away. So there's no need to panic. So. This is a joint work with Frank Hollander and Adrian Rowland. I will use the board for the first half of the talk because the subject is a little notation heavy. And it's good to let the notation sit on the board for a while before I play video games on the slide. So I'll keep the motivation simple. So we'll discuss, I'll give a brief introduction to dense graphs. So these come with, it's a very rich literature, so I'll present a very narrow view of this. Rather, our narrow view, I should say. So once I set up dense graphs and we understand what the dense graphs look like, I'll try and convince you that doing dynamics on them is a little hard. I mean, it's not hard to do dynamics, but to realize them as limiting dynamics is a little hard. It's a challenge. So dynamics on limiting dense graphs is a challenge. So this remains a challenge. I will present some results along these lines, challenges. And then I'll try and conclude with some very nice examples that we have got, examples of dynamics. So. And this will require some introduction to population genetics, but that I will use the slide. I will not use the board. So that's broadly the plan. I'll be a bit sketchy on details, but if it's not clear or you think I'm making an error, please ask me. I'll try and rectify it. So, like I said, I'll just begin with a very narrow introduction. So it's like, so Adrian and I thought about it like this, and this is what we focused on, and then Frank also likes the viewpoint. So here's the introduction. So this is the theory sort of exploded after a classic paper by Lovász and Szegedy in 2006. So this is the viewpoint I will start from. Of course, probabilists also like a very nice exposition by Diaconis and Janssen in 2008. This uses the Aldous-Hoover theory of exchangeability, which I will not focus on in this talk. So this I will sort of think. Of course, the literature is huge. There's several contributions. So I will, like I said, in my narrow view, I'll just try and get to this work and then sort of start from there. So what's the basic idea? So the basic idea is the following. You have n vertices, and your graph has lots of edges. And that's when you call a graph dense. So the idea is that, let's say you have a vertex at V, 1 up to n, and you have a graph Gn. It's a graph on V. Is dense. So that's the crucial terminology I'll keep using again and again. If it has lots of edges. So lots of edges means that if it has order n squared edges. So if the number of edges, so I'll just leave it a little loose, it's order n squared. So there are, so order n would be a sparse graph and so on and so forth. Bounded degrees are very, very sparse graphs. But a dense graph means it has lots of edges. because there are n choose 2 possible edges, and you have order n squared of them. So now, since my objective is to build some sort of dynamics on this, we must know first how to understand when two graphs are close by or when two graphs are far away. That's the first thing I like to understand. So this is the first definition. The next thing you have to understand is some notion of distance. So I will, okay, I'll just call it, okay, maybe I'll call it that, a notion of distance. So I'll just leave it as metric. So you need a metric space structure on graphs to sort of understand how to do dynamics. So notion of distance. So here, so there are various ways of defining distances on graphs, but here what we'll do is I'll try and understand structural properties of the graph. So I'll say two graphs are close by if they have similar structural properties. So by that I mean the following. What I will do is we'll take F to be a finite graph on k vertices. And then what you'll do is you look at the number of copies of F in Gn. Okay. So that's like you can just look at the number of copies of F on Gn. Let's say k is much smaller than n. So let's say k is 2, then you're just looking at the number of edges in Gn. If k is 3, perhaps the number of triangles in Gn. And so on. But of course, this can vary. So you want to make a density. So you just normalize it by the number of copies of F in the complete graph K. You just normalize it. So Kn is a complete graph, and then so you do a standard n. It's like order n power k at the bottom. You have this. So this you call as the subgraph density. So you call this as TF. So since the density it's between 0 and 1. So these are called. I mean, there are various ways in computer science. They're called fingerprints. So I just call them subgraph densities. So once I have a notion of subgraph density, I have two graphs. I look at how the subgraph densities differ to quantify a notion of distance. That's what I know. So what you do is the following. You take your favorite enumeration of graphs. So enumeration. And again, the idea is that I'm not concerned about the labeling of vertices or how the vertices look like and so on and so forth. So all graphs are the same up to graph isomorphisms for me. So I'm in some equivalence class. I'm only looking at structural properties like subgraph counts. So what I'll do is I'll fix my enumeration. And let's say I have two graphs. Say that I have two graphs, Gn and Gn prime, on n vertices. If I want to know the distance between them, what I do is I look at TFI Gn, so the density of Fi in Gn. I subtract it from the density of Fi in Gn prime. So that gives me some notion of how different the graphs are. So one, if I is equal to 2, you can look at edge density and so on and so forth, triangle densities and so on. Of course, and then you want to sum over I. Of course, these are all less than 1. So this whole thing is less than 2. So if you want to sum them up, you just normalize it by 1 over 2 to the I. So and that's what I'll call as the subgraph of Gn. Enumeration of all finite. Yeah, just enumerate. Your favorite enumeration, I think. So this is not quite a metric because, like I said, it's metric up to this isomorphism class ideas. I will just sweep under the carpet. I will not discuss it in detail. But you take you line up all finite graphs, have your favorite enumeration. You keep it in hand, and then with that you work with the thing.
That's countable.
That's countable, yes, right.
Is there finite graphs with at most k vertices or
all finite graphs? All finite graphs. Yeah.
So this depends on the numeric.
Right? So everything's up to isomorphism classes. So motor. Yeah, okay. If you agree that this is a metric up to something, it's okay. Yeah. If you go to the equivalence classes space, then I think it's okay. You take every graph as part of an equivalence class, and on the equivalence class space is a metric.
it's a metric?
Yeah. Yeah, it doesn't matter. It doesn't matter. So one of the key things is that if I have a sequence of graphs on this metric space, what are its natural limit points? Where do they go? Do they just, if n goes to infinity, where is the graphs going in this metric space? Are they just flying away, or what's happening? One natural thing. So towards that, there's an object. There's a third object I would define, which is called Graphons. Graphons, which is the title of my talk, Graphon dynamics. So these are, by definition, just symmetric functions on the unit square. So that's any symmetric function measurable, that's called a graphon. Okay, that's his definition of the graphon. And for any graphon, I'll define it abstractly right now, and I will come back and connect it up. You can define a subgraph density for a graphon. So TF kappa is just the integral on the unit square. Let's say F has k vertices again. Let's say m vertices, let's say. So F has m vertices. So 0, 1 to the m dx, and this product of over all I and j, just edges in F of kappa xi xj. Okay. So that's the function k or kappa, how we want to read it. That's the definition of TFK. So this has an intuitive meaning. I'll come to it in a few minutes. But as of now, that's the definition. It's just the m-fold integral of this functional. You take kappa xi xj over all edges of F. So E of F is just the edges of F. So what happened was that the theory exploded because of the following result in the paper I mentioned. So this is sort of a major theorem in this field. Due to which all the structure makes sense, is in the following sense. So it essentially characterizes all limit points. This is Lowas and Segedi in 06. So I'm stating it a little imprecisely, but the philosophy is close by. So if Gn is a Cauchy sequence of dense graphs, in this D submetric. So it's a Cauchy sequence. Then that means these are, as n gets larger and larger, they have similar subgraph densities and they look structurally alike. Then they come from a graphon. So then there exists graphon kappa such that you look at the subgraph metric of Gn and kappa. So when I say D sub Gn kappa, I just, in this I put TFI kappa, and TFI kappa is by this definition. So this goes to 0 as n goes to infinity. This was the sort of the major theorem that came out in 2006, that everything came from one function like this. So. Yeah, so it's unique up to measure present transformation on the square. Yeah. Because this statistic, if I do a measure present transformation, the statistic will not change. They are this dxi, right? So this should be, if you want it precisely, then the way you write it is just a product, what k equal to 1 to m, or j equal to 1 to m of dxj. The m-fold integral. Yeah, so that's right here, right? So I and j are an edge in EF. You take that xi coordinate and xj coordinate.
What is the motivation behind the definition?
Yeah, I'll come to it. I'll sew it up in a second. Yeah.
Basically, the probability of seeing them.
Right.
So the subparameter.
Yeah. I'll come to it in a second.
To get overall.
No, I'll just.
Overall edges, probability is 0.
So, like, just to get to what Remco was saying, I'll just. So this is the major result, that these graphons are the limit points of this dense graphs. Okay. So that's where the graph theory is at. But as a probabilist, I'd like to sort of interpret this in a way that sort of makes sense and statistics make sense. So what you do is you try to understand how to construct. So you have a sequence of finite graphs going to a graphon. You go the reverse way first. You say how to construct finite graphs from graphons. So I give you a graphon. What sort of finite graph does it represent as n gets larger and larger? Let's try and think about that. And then we'll understand this statistics better as well. Then the idea is that I have kappa from 0, 1 squared to 0, 1. I have n vertices, 1 up to n vertices. So what you do is you give each vertex a label, a uniform random variable label. So you get u1 up to un, you give them uniform IID labels, uniform 0, 1 IID labels. So you give each vertex a label. And the label is a uniform random variable in 0, 1. And then what you do is you have a vertex I and a vertex j. You connect an edge with probability kappa of ui uj. So you give an edge to between two vertices with probability kappa ui uj.
Not directed.
See?
It's not directed.
No directed edge, just edge you bring on. Yeah, everything's independent. Everything's independent. Independent. So independence here is crucial, but of course in my dynamics that may not happen, but yeah. So that's how you think of a finite graph from a graphon. Okay. So before I go to my slides, I just want to do a bunch of examples and connect to that statistic. So here the idea is the following. So now suppose my kappa was a constant function p. Okay, so kappa was a constant function p. That means I'm connecting every edge with probability p. So I'm just getting the Euler-Shreni graph back. So this is called, let me call this a G and K, these finite graphs. And this is the Euler-Shreni graph. So Gn, that's the GNP. So then what I can also do is, I can do many things. So let's say I have two groups. One group A, I have another group B. So I have some vertices here. I have some vertices here. What I can do is, if I connect edges here with probability, let's say beta, I have edges here with probability, let's say alpha, and I have between them, I have an edge with probability delta. So I have a graph like that, right? So that would come from a graphon of the following kind. So I'll have a box like this. I think I have space here. So a box like this. I have a square. I have a proportion of A is here, comma, and then all I'll do is I'll put alpha here, beta here, a delta, and a delta. So if my graphon looks like this on the unit square, 0, 1, 0, 1, with these values, that represents a graph like this. So these are called stochastic block models. So now this is the state, and then, oh yeah, so one, before someone asks question, so one way to understand this is the following, that, so if you look at this result right here, right, if you look at G and kappa, you're sampling uniformly from kappa in some sense. You can actually check that this G and kappa will actually converge to your kappa going to 0 in the subgraph metric. That is just a law of large numbers result. Because all you're doing is you're sampling from kappa, looking at the number of copies of these subgraphs, and this is just giving you the law of large numbers. And that you'll immediately spot if you just tweak the definition a little bit. Yeah. Again?
You have a metric.
Yeah.
The two things are different to G and kappa. The graph kappa is
That's right. That's right, yeah.
you have to leave that.
That's right, I've done that, right? So that's just, the G and kappa means what? TFI G, TFI kappa I'll put here. Right, so if you want to just be precise about it, this is how you do it, right? You say DG kappa is just the sum over I beginning equal to 1 over 2I, TFG minus TFI kappa. That's why I abstractly define TFI kappa right here. Yeah. Yeah. No, I view it, it's good. Again? That's random graph. It's random graph. It's a law of large numbers. It's almost surely. So it's almost surely it's true. But why is that almost surely true? Let me just finish 1 second, then I'll answer. Is that this expression right here, if you just stare a little bit, is just the expected value of the product of I and j in E of f of kappa ui uj. Once you just stare at this, that this is just exactly this expression, the law of large numbers is almost immediate.
Graphons will not just have convergent type graphs of T limit, right? They'll also have some deterministic graphs.
That's right, it could have. But every deterministic graph will have a random graph intertwined inside it by this mechanism. That's the... As of now, no, everything's up in the air. Yeah. Okay, so you're right. So for this, I might need extra hypothesis on kappa. You're right. You're right. Continuity hypothesis on kappa. Or continuity almost everywhere on the... You're right. That's right. So yeah, for this equality you need. Yeah, you're correct. Yeah. For here, I only need measurability symmetry. I will need. That's right. That's correct. I think so, but yeah. That's right. Bound random should be okay, but yeah, I think it's okay. It's a bound. I think it's okay. I think. Okay, so that's my brute force introduction to dense graphs and graphons. Okay, so now what I want to do is, I want to now go and start doing dynamics on them. So in such a way that I want to do dynamics on the metric space of graphons, but I want them to come from dynamics of GNs. That's the idea. And now the difficulties itself are kind of obvious here itself, that this step itself has a lot of averaging, like I've indicated here. So you must have dynamics that survive this averaging. That's important. Most dynamics in the law of the result will result in a deterministic flow in the limit. That's where we are at. Yeah. Yeah. Every n is an independent graph. G and kappa is an independent graph, right? So no, as of now, in my case, I'm not coupling anything. So I have a discrete dynamics that I understand. Will it give me a dynamics on the metric space? As n goes to infinity, will it survive? That's the question I want to address.
You want a non-degenerate.
Of course, yeah, that's right. Yeah, non-trivial diffusion, yeah, absolutely. So for this audience, I don't know if I should motivate the idea. So there's lots of interesting examples of real-world dynamics floating around. But largely the mathematical treatment of dynamics has been in the sparse setting. the dense setting is still just about getting its attention. Because of this averaging effect that I mentioned, it's hard to produce a random dynamics in the limit. Because you have an almost sure limit to a graphon, and then in this almost sure limit, you're averaging a lot of things. If you have some edge dynamics, the edge statistics are being averaged out in some sense. And then you have to be careful how to sort of do this. Yeah. So second order fluctuations is still a largely open question in some sense. Though with Stein's method, you can do something, but CLT is still largely open. There's a lot of work in sparse literature, which I will not discuss, which is very different from this. Mixing time random walks studied. You play with the dynamics of the graph, and then you understand mixing times, how mixing times speed up, and so on and so forth. But the dense network is in its early stages. So let's see. So like we all know, it's if I give you a graph G sub n, you can define your favorite dynamics. You can say, okay, at some exponential clock, something's going to go on, something's going to go off. You can define various dynamics you want to define. But they may not survive in the limit. They may give you a deterministic flow typically. And it's been a challenge. So Harry Crane was the first to attempt this. He used the Aldous-Hoover theory. So what is that? So you can construct graphons or limits of dense graphs using exchangeable arrays. So you can encode the n going to infinity limit into a large exchangeable array. So that's what Diaconis and Janssen showed, that they're both equivalence ways of understanding the limiting object. And once you have an exchangeable array in the limit, you can project it using what's called a modulus map to get the graphon. That's a very sort of a strong theory built into this. So Harry Crane tried to use the theory because he came from the statistics viewpoint and he wanted a coupling as n gets larger and larger. So he tried to use the exchangeable theory to get a dynamics in the limit. Okay. But what happens is that when you project it back to the graphon space, you essentially get processes of bounded variation. You don't get diffusions. He doesn't get them. So he'll only get deterministic flows or jump processes, but not a diffusion like we think it is. Because the projections, you lose out a lot of things. You can write out a simple example to show that. I will not do this. So Anton, who's here in the audience, he and Jared Cerny wrote a nice paper explaining Crane's work, and I also have explained some extensions from his work as well in this idea. But in this setup, you'll only get deterministic flow, the jump process, but you do have the advantage of coupling. So your n graph and n plus 1 graph are internally consistent. In my case, I don't really care. I'm only looking at how the graph looks like. And n plus 1 can be very different graphs, but they'll have similar structures because they come from the same graphon. But an edge in Gn may not be there in Gn plus 1. But in this structure, in the exchangeable theory structure, you can maintain that coupling. But then you lose out, you don't get interesting process in the limit. Okay, so like I said, diffusions are not captured through the lens of Aldous-Hoover theory. So then the question is, are there no diffusions on graphons that come from discrete dynamics? Of course, you have a metric space, you can have some diffusion, you can abstract define a Markov process on it. But does it come from an interesting discrete dynamics? So like I said, the n go to infinity setting has a lot of averaging, and you take a typical intuitive dynamics, so whatever you want, on and off, or whatever, it'll just vanish the limit. You get a deterministic flow. Get an ODE. You won't get a nice, interesting random process. So you have to do something drastic. So what's like I said, the key thing is that what you will do if you want to do dynamics, you have dynamics on G and T, you want to produce a dynamics on HT, which is a limiting graphon. You will look at the subgraph counts at G and T, and then you'll hope that they stay as you let the n go to infinity. And then you hope that this averaging will not sort of worry you. So in this setup, the whole independent structure was there, so you could have a normal law of large numbers effect. If you have dependencies, what you have to do first is that you take the subgraph count, you do a concentration to the mean, and look at the mean statistic, and show it has some, it's like close to U statistic, but not quite. and that will give you a limiting object. Okay, so the proof is not straightforward even in a sort of a static setup, but that's how one would do it. Okay. If you sample the vertices in some way and then have dependency, then you'll be a little careful. You can't.
Do a second order thing also?
Second order is, like I said, this is only in some cases of like the independent cases you can do Stein's method and get CLTs, but otherwise it's not. There's also a random matrix version of this. So people say there is a random matrix version that has a CLT, but I'm not sure. Because TFGN is a random matrix sort of computation. So now let's try and do a simple example. Let's try. So let's try and take the stochastic block model. Like I said, I take this graphon. If I want to think of graphons, if I want to think of dense graphs, I think of a graph with h probability h of ui uj, where h is given by this function. So wherever the uij's fall, they'll determine the types, and that will give you the. Oh, I want a diffusion like this, let's say. Let's say I want to get a diffusion in the limit like this. So I want this diffusion to be like y1t is this point with the proportion of type A, let's say, and this yt is jiggling around. So the entire pink line will jiggle around, right, like a diffusion. It's a symmetric graphon, so this point here will jiggle like a diffusion on the diagonal. And I want y1t to move like a diagonal. So let's say I want to do that. So I have this deterministic model where I have gamma as the proportion of types. And now here I want this y1t to jiggle around, like a diffusion. So the graphon, this you can just think a little bit, it's immediate that the graph distance is determined by the proportion of types in some sense, all subgraph counts. So the subgraph counts will be diffusive if y1t is diffusive. So in that sense, this is a standalone as a graphon is diffusing in the D subspace. But can I get a discrete dynamics that gets to this idea? That's what I want. So like I said, natural ideas will give you deterministic flows. It's not quite clear. Something more drastic needs to be done. You can't sort of just do deterministic dynamics. So what you do is you just go to population genetics. Okay? So you brute force impose an extra randomness on the vertices. Okay? You think of vertices of two types and assume the types are changing dynamically and the connections are changing according to the types. Okay? Let's do a simple dynamics. So you take the classical Moran model. Each type is 0 or 1. At rate 1, you sample from the population and adopt the person the type of the person whom you sampled. It's a simple type. You look at the proportion of types, that goes to Wright-Fisher diffusion. This is one thing. So that's the population genetics model. So there's types moving around, and then each type imitates whomever it chooses. Right? So it's a very popular model in population genetics. It gives you simple diffusion, nice tractable one, stays between 0 and 1. So you have a diffusion in mind and you have a discrete object in mind. You know what you do is you look at the graph dynamics. You look at every time S, you take two vertices, you look at what types they are. They're same type, you connect them. They're not different types, you just leave the edge open. So it's a bipartite graph with only two blocks. But the types are changing, so the things will keep moving around for each fixed time. So the graph will move around. So now you look at TFGNS, right? So that's just the number of copies of F, complete graph. It should be of this order, but okay, broadly it's equal to. So you can just compute the number of copies of F in GNS. Since each block is a complete graph, because everybody's connected each type, you just get an expression of xn to the power k here, and n minus xn to the power k here. Because they're both complete graphs on each side, each within each type. And n to the k. So now if you look at it, you just rearrange the algebra a little bit. By the diffusion theory in population genetics, this goes to ys, and this goes to 1 minus ys. So now I know how the subgraph counts are converging. But then if I stare at it a little bit like this a little bit, this is just the subgraph count of the graphon, of this graphon, where ys is this. So I have a foothold now. So I know how to, there's one easy foothold to create dynamics. You put types on the vertices, You let the type jiggle around, you connect probabilities depending on the types. And that sort of sticks in the limiting dynamics. Of course, it's a product measure, so I'm cheating a little bit, but broadly, that's the idea. Just edge alone will not give you that, but some extra on top of it will give it. That's it, I'm almost there. So now, all I have to do is now set up the theory correctly now. So I have an example where I've shown you subgraph counts converge. Of course, subgraph counts converging doesn't mean the process is tight or the process converges weakly to the Graphon space. All that's not clear. So you have to set up the theory correctly. So you set up the theory correctly is quite fairly. So you understand that your subgraph counts converge. Then you also know that the filtrations are all adapted, the process is all adapted to the filtration of YS, because YS is alone determining how this HS looks like. That comes for free. And whatever the modulus YS has is transferred to TFH, and that biometric is transferred to H. So you get a diffusion on the Graphon metric space by this idea. So now here are the results. I'll state them in words. So the first result is you set up convergence on Graphon space. You identify when will a sequence of graphs go to your Graphon. So we luck out somehow. If you know subgraph density converge, and you know there's not tightness of just the individual ones, but sort of joint tightness, then you get process convergence in Graphon space. That's one result we have. That's the first result you show. You show how to show Graphon convergence, weak convergence in Graphon spaces. So both discrete graphs and Graphons go to Graphons. So it turns out these fingerprints are good enough at the weak level. Again, you will lose out the Aldersworth theory of couplings, but that's something else. Then here are some examples. The first is what I said. I gave you a single type one. You can do a multi-type Moran model to get a multi-type diffusion. You can let the probabilities vary in time. You can do anything you want, because the types determine the connections, and how the types change will determine how the structure changes. And by this idea that I shared, it'll pass on to the limit. Then one might think that, okay, you're only going to get stochastic block models. You're not going to get general Graphons. But then you're in luck, because in population genetics, there's a theory that goes to this Fleming-Viot model as m goes to infinity. You can let the whole thing as m goes to infinity. You get a genuine Graphon, which is fluctuating both on the square and on the sides. And it's also diffusing, according to how Fleming-Viot diffuses. So you get a true diffusion, which is sort of well beyond the stochastic block model framework. So it's not just block model, you get much more examples. And then you can jiggle little things to it. You can get very, very interesting examples. Because depending on the application, you'll have to see what comes from a nice, interesting application. But theoretically, now this theory is set up, at least in the subgraph convolution. So I'll just conclude a little bit. So the way I presented a narrow view of Graphons, and I presented a narrow view of dynamics to get the idea across. But these diffusions are not necessary. So you can take any dynamics in which the particles or types in some sense determine how they're connected. Those will generally carry through. As long as those have a diffusive limit, the structure will carry through. But I hope it's clear that you're making lots of changes. Okay? You're not making edge on off. That will not see the limit. You're making order n squared changes at each sort of broadly in some finite interval to get you an interesting limit in the end by this sort of thing. And there are several immediate inline available. We have written it out. You can write a formal generator for this Markov process. Interesting ones you'll get for specific models. It's just a beginning. It's not, I don't know, one needs to sort of see how to get back the discrete stuff, properties from the limiting dynamics. It's like, yeah. I think there's lots to be done. Thank you for listening.